Dear students, in today's lecture we will study about equivalent circuit of induction motors. Equivalent circuit of induction motors is a singly excited machine. So an induction motor is a singly excited machine, unlike a synchronous generator, which is a doubly excited machine. Since power is supplied only to the stator circuit in this case, not to the rotor circuit. So we begin with the transformer model, since this is very close to the transformer model. So we borrow the transformer model to design and model a circuit for the induction motor. First we get the transformer model, then we include the variable frequency and other similar induction motor effects. This E1 and ER are coupled with each other by an ideal transformer with effective ratio A effect. Since there is an air gap in an induction machine, the reluctance of the flux path is increased. Because of this air gap and the increase in the reluctance, the magnetomotive force of this induction motor is quite lower than that of the transformer model. In this diagram, the y-axis shows the flux and the x-axis shows the magnetomotive force. The coupling between primary and secondary winding is reduced. Due to higher reluctance caused by the air gap, higher magnetizing current is required to obtain a given flux. So if we want to get some particular flux, we need a higher magnetizing current. Therefore, the magnetizing reactance will be much smaller. The voltage ER produced in the rotor in the turn produces a current flow in the shorted rotor circuit of the machine. Now we consider that how the slip effect is having a role on the induction of voltage. In an induction motor, when voltage is applied to stator winding, a voltage is induced in the rotor winding of the machine. So the greater the relative motion, which means that as the greater the difference between the magnetic field and speed of magnetic field and speed of rotor, between rotor and stator magnetic field, and the greater the resulting rotor voltage and rotor frequency. The largest relative motion occurs when the rotor is stationary, which means n of m is 0 and n of sync is something. So n sync minus 0 is n sync, called locked rotor or blocked rotor condition. So the condition where the rotor is stationary is called locked rotor or blocked rotor. The smallest voltage and frequency occurs when the rotor moves at the same speed as the stator magnetic field. So both the speeds are synchronous, resulting in no relative motion. The magnitude and frequency of the voltage induced in the rotor at any speed is proportional to the slip of the rotor. So as the slip, if the slip is more, it would be the magnitude and frequency of voltage induced would be more. Similarly, if slip is smaller, it would be smaller. An induction motor equivalent circuit differs from a transformer equivalent circuit primarily due to the effects of varying rotor frequency on the rotor voltage ER and impedance RR and XR. So these are the three parameters. Because of them, the circuit is quite different from the transformer equivalent circuit. The frequency and magnitude of voltage induced on the rotor at any slip can be defined by F of R S F of E, or E of R S E of R naught. This E R naught means that this is the rotor is at stationary stage, or can be said as magnitude of the induced voltage at locked rotor condition. So naught is usually used for zero speed or stationary speed. The rotor resistance is independent of slip. The reactance of the rotor depends on the inductance of the rotor and the frequency of the voltage in the rotor. So this reactance is directly proportional and dependent on two main factors. One is this inductance, and the other one is this frequency. Frequency can be written in the form of 2 pi f, and similarly the whole reactance formula can be written in terms of S into XR naught, where XR naught is the blocked rotor reactance condition. The resulting equivalent circuit is something like this, where impedance is this constitutes of this inductance and resistance, and this is the voltage source ER. But we know that the rotor current in this circuit can be written as something like this, from obtaining the values from this circuit by putting voltage over impedance equal to the IR. IR is the current passing through this loop, and the IR becomes something like this. In terms of S, it can be simplified as this equation in blue color. But in this case, the denominator is now equal to the impedance or new impedance at the stationary stage. If this is the impedance, then the modified equivalent circuit can be written in the form of the new impedance and the new voltage. So the equivalent rotor impedance is this in this case. The rotor current as a function of rotor speed can be shown as something like this. This is the rotor current. It would be maximum at 0 speed, 0% of synchronous speed, or you can say that when the rotor was stationary, and it would be 0 when it would have 100% of synchronous speed, or we can say the speed is totally synchronous to the speed of magnetic field. Notice that at very low slips the resistive term Rr over S is very large than X of R O. So the rotor resistance predominates and the rotor current varies linearly with slip. At high slips, XRO is much larger than RRS and the rotor current approaches a steady state value as the slip becomes very large. So slip becomes very large when it is at the stationary stage. Similarly, slip becomes very low when there is very less difference. To produce the final equivalent circuit, refer rotor part of the model to the stator side. To produce the final equivalent circuit, refer rotor part of the model to the stator side. The rotor circuit model has all the speed effects concentrated in the impedance term. As we seen in the last chapter, that in the case of the transformer, the secondary and primary voltages can be written in terms of each other. The primary voltage was equal to A into secondary volt. Similarly, primary current was equal to secondary current over A, and Zs bar was equal to A square of Z of S. Same transformation can be applied to induction machine. So we can find E2, I2, E1, etc. So in this case, it can be seen that E1 can be written as A effect of E R naught I2, similarly Z2 and R2 is equal to A effect square RR, which is quite similar to the transformer case where we studied that Z of L or ZL bar is equal to A square into ZL, something like this. So this is a replica of that transformation. The per phase equivalent circuit of an induction motor becomes something like this, and from here we can find the values of the parameters, and the rotor resistance RR, the reactance XR naught, and the effective turn A effect are very difficult to determine on a cage rotor, but we can find the values of R2 and X2. But finding the value of RR, XR naught and A effective is quite difficult, and even though RR, XR naught and A effect are not known separately. So finding them separately is quite difficult in this case. So we manage how to find R2 and X2 in this equivalent circuit. This is for today. Thank you.